Hello and welcome to Unit 4.1, Radian and Degree Measures. In this lesson, you should learn how to describe angles, how to use radian measures. You should also learn how to use degree measures and how to go back and forth between degrees and radians. And lastly, you are also going to use angles to model and solve real-life problems. First, let's start by reviewing what are angles. Remember that an angle is always going to have an initial side, and then it also has a terminal side, which is rotated by the vertex of this angle. In pre-calc, we are going to place our angles in a coordinate plane, where the initial side is going to be on top of the x-axis, and then the terminal side is going to be the part that moves freely. The vertex is directly on top of the origin of our coordinate system. If that is the case, we have two types of angles. We have positive and negative angles. Positive angles are going to occur whenever we rotate the terminal side in counterclockwise position. If we rotate a terminal side in clockwise position, we will end up with a negative angle. Usually, we label angles with Greek letters such as alpha, beta, or theta. We can have two angles that have the same initial and terminal side, yet a different measure. For example, in this picture, you see that angle alpha is positive, while angle beta is negative. Both of them have the same initial and terminal side. Once again, such angles are called coterminal. In the second picture, you can see angle alpha is less than 90 degrees, while angle beta is a full rotation of 360 degrees, and then the measure of angle alpha. Once again, coterminal angles. Radian measures is another topic that we started looking at already. When we talk about radians, it is simply a different way to measure an angle. In order for us to use radians, we use the radius as a measure alongside the arc. The official definition of a radian is that 1 radian is the measure of a central angle theta that intercepts an arc, S, equal in length to the radius, R, of the circle. Algebraically, this means that theta, the angle measure theta, is equivalent to the intercepted arc divided by the radius. Because the circumference of a circle is 2 pi r units, it follows that a central angle of 1 full revolution corresponds to an arc length of S equals 2 pi r. This is a really important formula right here that we're going to come back to and see at the end of this lesson once again. So just remember, a full revolution corresponds to 2 pi radians. We can see that a little bit easier in this circle. If we take a radius length and lay it along the arc of a circle, we'll be able to lay a little bit more than 6 radians, to be exactly precise, about 6.28 radians, or exactly 2 pi. Now, since we are putting our angles in the coordinate plane, it would be important to remember the name of our quadrants. Anything in here is quadrant 1. This is going to be an angle measure between 0 and pi over 2. Our next quadrant is quadrant 2, where we have angle measure between pi over 2 and pi. Then we move on to quadrant 3, where our angle measures would be between pi and 3 pi over 2. And lastly, in quadrant 4, we have angle measure between 3 pi over 2 and 2 pi. Another thing to remember is that if you have an angle whose terminal side falls in quadrant 1, typically this is going to be an acute angle because it is less than a right angle. If, however, the terminal side is in quadrant 2 and the value of this angle is less than pi, then that would be considered an obtuse angle. We already talked about the coterminal angles. An easy way to remember of how you can find coterminal angles is just add a full revolution. That means that to any given angle, say pi over 6, we can add 2 pi, or we can add 2 times 2 pi, which is adding 4 pi, because that adds 2 full revolutions. Now I'm able to find 3 different coterminal angles. I have my starting pi over 6, then I would have 13 pi over 6 when I add 2 pi, or I can have 25 pi over 6 when I add my 2 full revolutions. Remember the coterminal angles could also be negative. That means that I could start with pi over 6 and then I could subtract 2 pi so that I can get a coterminal angle. Such an angle would be negative 11 pi over 6. Here's an example. We're given a figure of an angle. In this case, our given angle is actually 13 pi over 6. We're asked to find a coterminal angle. We can take our 13 pi over 6 and subtract 2 pi to find a coterminal angle of pi over 6. In this example, we're given a positive angle theta equals to 3 pi over 4, and the angle is drawn here in the picture as well. If we wanted to find a coterminal angle, in this case, once again, we're going to subtract 2 pi so that we can go in the negative direction instead, and we can find a coterminal angle with a value of negative 5 pi over 4. Another example, in this case, we start with a negative angle. Theta this time is equal to negative 2 pi over 3. This lands the terminal side in quadrant 3. If we wanted to find a coterminal angle, we would take this side and imagine rotating it around in the positive direction and bringing it back to its original place. Essentially, I just described that I am adding a full revolution, or add 2 pi. That gives me 4 pi over 3 for a coterminal angle. A more common way of measuring angles, and a method that you have been using so far, is the degree measure. The degree measure takes a full circle and it breaks it down into 360 degrees. Once again, in pre-calc, we will be placing our initial side on the x-axis. This will be our 0 degrees, and then we move in the positive direction, which is counterclockwise direction, to complete a full circle or a full revolution of 360 degrees. Since we already talked about 360 degrees is equivalent to 2 pi radians, we can simplify this a little bit since both of those are multiple to 2, and we can get the formula that 180 degrees are equivalent to pi radians. This is a formula that we are going to use when we convert from degree to radians. If you wanted to convert degrees to radians, multiply your degrees by pi radians and then divide by 180 degrees. If you wanted to do it in the opposite order, convert radians to degrees, then multiply the radians by 180 degrees and then divide by pi radians. In the next picture, you can see a few translations between radians and degrees, and you can also see some standard angles that we will be using quite a lot in this upcoming week. Here's an example on converting from degrees to radians. If we start with 135 degrees and we wanted to convert to radians, we're going to multiply by pi radian and then divide by 180 degrees. And instead of trying to remember two formulas, you can just ask yourself, I'm trying to cancel out my degrees. How can I do that? Well, you have to divide by the degrees and then use your common 180 degrees is equivalent to pi radians. Another review in terms of degree measure is what is a complementary and a supplementary angle. Remember that two positive angles, alpha and beta, are called complementary when their sum adds up to 90 degrees or pi over 2. Two angles alpha and beta could also be supplementary angles if their sum adds up to 180 degrees or adds up to pi. In this example, we're asked to find the complement and supplement for each angle. If you have 72-degree angle, its complement should add up to 90 degrees. So take 90, subtract your angle, and you have found your complement. To do the supplement, start with 180 degrees, subtract the given angle, and you have found the supplement. I'm going to let you read over the other two examples through the PowerPoint. Another really important topic is the linear and angular speed. One of the first things that we start with is how do you find an arc length? For any circle with a given radius r, the central angle theta intercepts the arc. You can find the arc length using this very simple formula. S, the arc length, is equivalent to the radius multiplied by theta, where theta should always be given in radian measure. Let's take a look at an example. Here we have a circle with a radius of 4 inches. We're asked to find the arc length intercepted by a central angle of 240 degrees. We are going to use this formula. Arc length is equal to the radius times theta, where theta is in radians. First, we have to convert 240 degrees into radian measure. We do that by multiplying by pi, dividing by 180 degrees. 240 degrees is equivalent to 4 pi over 3 radians. Now to find the arc length, we are going to substitute into our formula, where the radius is 4, the angle measure is 4 pi over 3. That gives us 16 pi over 3. And if we wanted to find an actual final answer, we can, or approximate answer, we can input that in the calculator to see that this is approximately 6.76 inches. Now for the topic of speed, linear and angular speed, I'm going to attach a second video.